Here's an impulse and momentum problem. I recommend that you pause the video at the problem statement and then work out your solution before you watch mine.
Okay, here's another one for you. This is another golf ball problem. Interesting. Golf ball sits on a tee awaiting its fate to launch at 35 meters per second. Golfer exerts a force. So here we have a golf ball sitting on a tee. Here's the golf ball. There's a tee underneath, like so. Golf ball has all kinds of dimples to it, like that. And under condition number one, it's just sitting there doing nothing. It says it has 50 grams worth of mass. M is 50 grams. Good. In the second part, it says that the golf ball is launched. So now here's part two, golf ball. All the little dimples. And here it's being launched, and the launch is such that the velocity is 35 meters per second. In the meantime, what's happened to this thing is that there has been a force applied to this thing, force. And this force, it says, is 60 newtons. Great. 60 Newton force got applied to this golf ball. Okay, what is it that happened? That golf ball got launched at 35 meters per second. And the question it asks is, how long must the contact last to achieve this? So the unknown here is the delta t. How much is the delta t? Okay, do we have a physics principle for this? Yes, we do. This one is the one that's referred to as impulse momentum. And it works like this. Force applied multiplied by the time interval over which it is applied equals the change in momentum. F delta t equals m delta v. Great. So then, what do we know? What do we not know? We know F. We don't know delta t. We know m. And we know delta v. Haha. I think we're in business here. So now, we can find the delta v. According to this, after algebra, smoke and dust clears, it's F delta t divided by m. So then, we can do this by putting in the numbers. F delta t, oops, we don't want delta v. What do we want? We know delta v. We want to have delta t. Delta t is the unknown. Oops. See what happens sometimes? That's why it pays to look back at the diagram, because now you see from the diagram, we need a delta t. Turn the algebraic crank, and you never know what's going to happen. Delta t, it says, according to this, is m delta v divided by f. Now we'll see how we can make this go. M, what's m? This says it's 50 grams. Got to just write down 50 grams? It's not really in the right units, so what we have to do then is we got to change this on the side someplace and say 50 grams equals how many kilograms? Because we're trying to get this into the MKS system, because that's the easiest way to keep track of everything well. In order to do this, the kilo is a 10 to the third. So if we're trying to solve this for how many kilograms that is, we divide both sides by 10 to the third and say that question mark is 50 times 10 to the minus 3. Or the same thing as 5 times 10 to the minus 2, and these are kilograms. So now we'll put that in. 5 times 10 to the minus 2 kilograms times delta v. It says that's from 0 to 35 meters per second. So 35 meters per second, all divided by F, which it says is 60 newtons. So then we'll get a number coming out of this. It says 2.92 times 10 to the minus 2 seconds. Is that really seconds? Kilogram meters per second. Newton, kilogram meters per second squared. Second squared down below comes up the top. Seconds. Good. Suppose we hadn't changed those grams into kilograms. What would have happened? It would have been 29 seconds. Would that pass a reasonability test? 29 seconds. You got to hit a golf ball for 29 seconds. Well, if you ever watch golf on TV, maybe it seems like 29 seconds, but it isn't. It's way less than that. So sometimes the reasonability tests help you. Okay.